Now let's look at Cavalieri's principle. So Cavalieri's principle can be applied to two-dimensional figures and three-dimensional figures. I included a link in your packet to a couple of videos that describe it maybe a little bit better than how I might describe it, but it's a pretty straightforward concept. What it says is if you have two-dimensional figures and they have the exact same height and they have the exact same width at every point along the height, then they have the same area. So on this left-hand picture, we have a rectangle. Its base is 6, its height is 7, so the area would be 6 times 7, which is 42. Now to the left of that, we've got kind of this crazy looking shape, kind of looks like a wave, but you can see that the width is 6, just like the rectangle. And if I were to draw from any point across, it would be 6. Everywhere would be 6. So the width is going to be 6 everywhere along it. And the height of that shape, because it's perpendicular, is also 7. So even though that shape looks totally different, because they have the same base width all along and they have the same height, then they both have an area of 42. So on the right hand side, it says, according to Cavalieri's principle, which two of these shapes definitely have the same area? So in order to figure that out, we'd have to see which ones have the same height and which ones have the same width all along. So if you're comparing these individual widths, right? So those all look the same. But as you move up, when you get to the top, you've got this little guy, and then that much larger one. So there's no way that this shape has the same area as those two triangles. Those two triangles appear to have the exact same height, right here and right here, and it appears that their widths are exactly the same at every point. So these two will have the same area. In 3D, Cavalieri's principle pretty much means the exact same thing. So if you have two three-dimensional figures that have the exact same height and matching base areas at every point, then they will have the same volume. So we've got looks like a rectangular, maybe a square prism on the left-hand side. We know that the base area is 25 centimeters, and we know that its height is 10 centimeters. Then you have that cylinder on the right-hand side of it, and you know that its base area is also 25 centimeters, and its height is 10 centimeters as well. So even though those are two completely different objects, because they have the same base area and the same height, and the formula for both of those shapes is base times height, when you do 25 times 10, you're going to get 250 cubic centimeters for both of those 3D figures. All right, so in the picture on the right, it says which of these solids have the same volume? And down below, it says all three solids have the same height, which is important for Cavalieri's principle, and they have matching cross-sectional areas. So that means no matter where you go, every horizontal cross-section has the same area. So if they have the same cross-sectional areas and the same height, all three of them, then that means that all three of them are going to have the same volume.